In this video, we're going to look at more examples of conditional probability, more examples of conditional probability. So again, more examples of conditional probability. So let's go through this example. I've actually written it down to save a little time. I've written the problem statement down. So suppose there are bags of candy with 3 candy bars in each bag. And so you have, a bunch of bags, each with 3 candy bars. And the candy bars may be either Almond Joys or Snickers. Some fairly common candy bars. Like Snickers has traditionally been one of the most popular candy bars. And the probability that the bags contain 2 or more Almond Joys is 0.648. And the probability that the bag contains 1 or more Snickers is 0.784. So I called this, of course, Almond Joys AJ and Snickers SN. And the probability that the bag contains exactly 2 Almond Joys is 0.432. So those are probabilities. And suppose we peek into one of the bags and we see that one of the bars is a Snickers. So we look in the bag and we see, one of the bars is a Snickers, but we can't see the other bars, the other 2 bars in the bag. So what is the probability that 2 of the 3 bars in the bag are Almond Joys? Now we're told, that the probability of a bag has 2 or more Almond Joys is 0.648. So we could use that, but we have more information. We've peeked into the bag, and we see that one of the bars is a Snickers. So we can have a more accurate number for our particular case than this 0.648. So let's see if we can do that. Again, our goal is to find what the probability that 2 of the 3 bars are Almond Joys. Of course, what that means is, since we already know one of this is a Snickers, we're saying that what's the probability of the other 2 bars being Almond Joys? And so solution. So let's define some things. Let's define A, we'll call A is the event. Two or more of the bars are Almond Joy. And let's say B is the event. One or more of the bars are Snickers. Now again, I picked those 2 as our events because we were given those probabilities. We were given probabilities 2 or more being Almond Joy, and we were given the probability of 1 or more being Snickers. So that's why I picked those 2. Now, I think what we're going to need, we're kind of going to be asking what's the probability of event A, two or the more the bars being almond joy, given event B, because we've peeked into the bag and we know that there is one bar is a Snickers. So what's that probability? And we know the equations we're going to use. Let's maybe also make a little diagram. But sometimes books use these diagrams. So again, we have probability of A, probability of B, and then the probability of the intersection would be here. So again, we actually have all this stuff here. And now we know the probability of event A is 0.648. We know probability of B is 0.784. And finally, the probability of exactly 2 is 432. So we know, so again, of exactly 2 almond joys would actually be this intersection right here, wouldn't it? This would be 0.432, because that'd be the case we had 2 or more almond joys and 1 or more Snickers. Of course, what that really means is we have 2 almond joys and 1 Snickers, so that'd be that there. And so now we can calculate the other parts. So probably if 2 or more almond joys was this. So if we take 0.648 minus this 0.432, that's going to give us 0.216 over here. And this would be the probability of having 3 almond joys. Then also over here, if we take this value, we know probably 1 or more Snickers, 0.784. If we subtract this from 784, we get 0.352. And in fact, if you would add these up, you would get 1. So again, we're doing this calculation. Now we know we're given B, aren't we? We already know that we're given B because we stuck a peek and found that a Snickers, where there was a Snickers in there. So we know we don't have this part. This would be 3 almond joys. So we have this part. Now I'm sort of doing this visually. We're going to do it with equations here in a minute. 0.432, 0.352. And so we're really dealing with this probably. We're dealing with this right here. We know event B has already occurred, and we want to know what the probability of this also occurring over here. And so that's it pictorially. So let's actually calculate it now. So we know if we have probability of A given B, remember that's going to be the intersection of these two. Divided by the probability of this. And of course, the probability of the intersection of those two was this right here, 432. And the probability of B, of course, that was given the 784. Which, of course, is the same as the sum of these two. And when you calculate that, we get the probability of 2 almond joys being in the bag is 0.551. So again, this was our equation. Pictorially, it looks like this. Event B has occurred. And so what's the probability of event A occurring, again, which is just this part right here, given that B has occurred? So again, another way to look at this pictorially, it would be this part divided by the total, because you could add these two up and get that. Now, for some conditional probabilities, it's helpful to think of the events this way. So let's say if you have maybe one event A and A complement. Actually, let me just make this a little bit different. Say if you have, maybe an event here A and A complement. And then you have an event B. Say it's contained within here. This is the event B. And so over here, if this whole thing is event B, this is going to be B intersection A complement. This part over here is going to be B intersection A. And this picture can sometimes be helpful, especially if you're dealing with a problem where you're dealing with, say, one set has A and its complement. So let's take a look at this problem. Suppose the company regularly inspects lawnmowers that they use for their business. They have found that the probability that the blade is damaged is 0.15. And the probability the drive blade needs replaced excuse me, that the drive belt is 0.2. Then the probability excuse my writing there, I'm messing things up quite a bit. The probability the blade is damaged and the drive belt needs replaced is 0.08. Suppose that during the inspection of a lawnmower, it is found that the blade is damaged. What is the probability that the drive belt needs to be replaced? On the other hand, suppose that the blade is not damaged. What is the probability that the drive belt needs replaced? So let's take a look at this problem. And so as usual, it's good to sort of define some things here. Now, things that we have that we've been given are, whether or not the blade is damaged. So let me call B, the blade is damaged. And let me call DB the event drive belt needs replaced. And again, sometimes it's helpful maybe just to write down all the things that we have. So, so we know that probably that the blade is damaged is 0.15. So probability of B is 0.15. And the probability that the belt needs replaced is 0.2. Again, since this is sort of like a complement type problem, because we have the case where the blade is damaged and it's not damaged, we can maybe write down the other related probabilities. So the probability. So if there's a probability the belt is damaged, a probability that the belt is not damaged, which is B complement, is 0.85. And the probability the drive belt needs replaced, if this is 0.2, then that's got to be 0.8. And another thing that we have, the probability that the blade is damaged and the drive belt needs replaced is 0.08. Again, another thing that we can kind of look at here is that what I mentioned before, we're eventually going to be interested in the two cases where you have the blade is damaged and when the blade is not damaged. So it might be helpful. Again, maybe this diagram was helpful, maybe not, but we can put it down. Again, just what I was talking about a minute ago, we can have over here the event B, the blade is damaged, and over here the complement, the blade is not damaged. And then event DB, I say I made a mistake up here, by the way. This should be DB complement here, shouldn't it? Sorry about this. Notice up here, this should be DB complement. So down here, again, this is the event, say DB. This would be DB intersection BC. This is DB intersection B, like that. So we might be using that here in a minute. So let's try the first part of that question. The blade is damaged with the probability that the drive belt needs to be replaced. So again, that's going to be, we know that the blade is damaged, so that's the event we're calling B. And what's the probability that the drive belt needs to be replaced? That's going to be, remember, it's always the intersection of these two. Divided by the probability of this one. Now, these numbers we have all given, don't we? This is 0.08. And this is 0.15. 0.533, like that. That's part A. Now for part B, we know that the blade is not damaged. What is the probability that the drive belt needs to be replaced? So this time we need the answer to this question. The blade is not damaged. So be complement, yet the drive belt needs to be replaced. Again, that's going to be the intersection of these two. Divided by the probability of this. So this is what we're trying to solve, but we have this over here, but what we don't have is drive belt intersection B complement. In other words, the drive belt needs replaced and the blade is not damaged. So we're going to have to use our little diagram up here to find some of this information. So keep this in mind. We want to solve for this right here. But we need this here. And what we're going to have to do is work with this. So the probability that the drive belt needs replaced is going to be equal to the sum of these two. See, this is the total event for the drive belt needing to be replaced. That's going to be a probability of this plus the probability of this. So we can just add those two together. Drive belt intersection BC plus probability drive belt intersection B. And this is what we need right here because we want to plug it in here. So now over here, we know that the probability of the drive belt needs replaced is 0.2. And we want to solve for this. And we know probably the drive belt needs replaced and the blade is damaged is 0.08. And if we solve for this, then this is going to give us probability of drive belt intersection BC is going to be, I don't know why I put a parenthesis up here, but I did. So if we take this minus this, we get 0.12. Now we have this piece of data that we can plug into here. So let's go ahead and just write this all out. Probability that the drive belt needs replaced, given that the blade is not damaged, is going to be probability of the drive belt intersection B complement divided by B complement. Again, this right here is our 0.12. And this is 0.85. .14117. So that's the probability that the drive belt needs replaced given the belt is not damaged.